मोशन ऑफ चार्ज पार्टिकल इन इलेक्ट्रोमैग्नेटिक फील्ड। पहला केस, फर्स्ट केस इन यूनिफॉर्म E vector and B vector fields. In uniform electric field and magnetic fields, electric field is E vector, magnetic field is B vector. The force acting on a particle of charge Q in uniform electric field E is given by this formula, F equal to QE vector. If Q is positive charge, force acting will be in the direction of E vector. If Q is negative charge, direction of force will be opposite to the direction of E vector. Similarly, force acting on a particle of charge Q moving with velocity v in uniform magnetic field B is given by this formula, F vector equal to Q V vector cross B vector. If Q is positive charge, direction of F vector will be that of direction of V vector cross B vector. And if Q is negative charge, direction of F vector is opposite to that of direction of V cross B. Direction of V cross B is perpendicular to both V vector and B vector. And this direction of V cross B can be determined by law of screw. If we rotate a screw from the direction of V vector to the direction of B vector, then the direction in which this screw moves will give the direction of V vector cross B vector, and it is always perpendicular to both V vector and B vector. Now the force acting on a particle of charge Q moving with velocity v in uniform electric field E and magnetic field B is given by F vector equal to Q into E vector plus V cross B vector. Q E vector is force due to electric field E and Q V cross B is force acting due to magnetic field B. This force is known as Lorentz force. Equation of motion of charge particle can now be written by this equation: m into dv upon dt equal to q into E plus V cross B. Q into E plus V cross B is force F, and when we write equation of motion, we write this force equal to mass into acceleration. So it is equal to m into dv upon dt. dv upon dt is acceleration, and mass into acceleration equal to force. This is the equation of motion of charge particle under the action of Lorentz force. Now we take the first case when E vector is 0. That is, we want to study the effect of magnetic field only, effect of constant magnetic field on the motion of charge particle of charge Q. If electric field E vector is 0, force acting on charge particle of charge Q will be equal to Q into V cross B. It is the force due to magnetic field B. And equation of motion of charge particle can now be written as m into dv upon dt equal to q v cross b, or we can write it as mv dot equal to q v cross b. We write dv upon dt as v dot. Dot means differentiation with respect to t. If there is a single dot, it is differentiation with respect to t, and if we use double dot, it will be double differentiation with respect to t. So equation of motion, we write it as mv dot equal to qv cross b. V dot is dv upon dt, which is acceleration. So mass into acceleration equal to force, and this is the equation of motion. If magnetic field is along the direction of z axis, we assume direction of B vector as direction of z axis. Then we can write B vector as equal to B k cap. K cap is unit vector along the direction of z axis. And B is the magnitude of magnetic field. So if magnetic field is along the direction of z axis, we can write it as B k cap. We write unit vectors along the directions of x, y and z axis as I cap, j cap and k cap. So B vector is B k cap. It is along the direction of z axis. In this case, we can write V vector cross B vector as equal to this determinant. Any cross product of two vectors we can determine by using such determinant. We write a determinant. In first row we write I cap, j cap, k cap, which are unit vectors along x axis, y axis and z axis. In second row we write components of first vector, that is v vector here, and components of v vector are vx, vy, vz. So in second row we write components of v vector that are vx, vy, vz, and in the last third row we write component of this second vector b vector, and component of b vector are 0, 0, b, because b vector is b k cap. So we write b in third column. X and y components are 0, only there is z component, and value of that z component is b. If we solve this determinant, it comes out to equal to I cap b vy minus j cap b vx plus k cap 0. I cap, with I cap we have b vy, then minus j cap, with minus j cap we have b vx, and plus k cap, with plus k cap we have 0. So there are two components for v cross b. Z component is 0. So equation 5 can be written as this is equation 5, which is equation of motion mv dot equal to q v cross b. Now we write three equations for this single equation for its three components. For x component, in left hand side we write mvx dot. For y component we write mvy dot, and for z component we write mvz dot. And values of these three components, mvx dot is equal to qbby. See the value of determinant. X component is bvy. So mvx dot is equal to q into x component of v cross b, that is bvy. So mvx dot equal to q bvy. Similarly, mvy dot equal to minus q bvx. With q, here we write y component of v cross b, and y component of v cross b is minus bvx. Then we have this second equation, mvy dot equal to minus q bvx. Similarly, z component mvz dot is 0, because z component of v cross b is 0. So we now have three equations which are equation of motion in terms of vx dot, vy dot and vz dot. If we differentiate equation 6 with respect to t, if we differentiate this equation mvx dot equal to q bvy, this is equation 6. If we differentiate this equation 6 mvx dot equal to q bvy, then we get mvx double dot. Vx dot becomes vx double dot. One dot is increased. One dot represent one differentiation with respect to t. So differentiation of vx dot with respect to t becomes vx double dot. And in right hand side we have qb vy dot. Differentiation of vy is vy dot. Similarly, by differentiating with respect to t, the other two equations we get mvy double dot equal to minus qb vx dot and mvz double dot equal to 0. Now from equation 9, is this equation mvx double dot equal to qb vy dot. From this equation 9 we write vx double dot equal to qb upon m vy dot. Put m, bring m to right hand side. So vx double dot is equal to qb upon m vy dot, and it is equal to qb upon m, and we put the value of vy dot. Value of vy dot is here in equation 7. Equation 7 gives value of vy dot, and this value of vy dot is equal to minus qb upon m vx. We substitute the value of vy dot from this equation 7, and this value of vy dot is minus qb upon m vx. Then vx double dot now becomes equal to qb upon m into minus qb upon m vx. Minus is taken outside and qb upon m is 2 times. So we have minus qb upon m square vx. Vx double dot is equal to minus qb upon m square vx. Similarly, from equation 10 we can write for vy double dot. Vy double dot from this equation is equal to minus qb upon m vx dot, and we put the value of vx dot from this equation, that is equation 6. From equation 6, value of vx dot is qb upon m vy. We put this value of vx dot here. Then we have for vy double dot equal to minus qb upon m into qb upon m vy, that is minus qb upon m whole square vy. From equation 11 we have Vz double dot equal to 0. This is equation 11. Vz double dot is 0. There is no force along the direction of z axis. So acceleration along the direction of z axis is 0. Equation 12 and 13 describe simple harmonic motion with cyclotron frequency omega c equal to qb upon m. These are the equations 11 and 12. Equations 12 and 13. Equation 12 gives Vx double dot equal to minus qb upon m square Vx, and equation 13 gives Vy double dot equal to minus qb upon m square Vy. This term qb upon m whole square is same in both the equations. First equation is for Vx and Vx double dot, and second equation is for Vy and Vy double dot. We write this term qb upon m whole square as omega c square. So we write omega c as qb upon m, and we write modulus of q. Modulus of q means we take only magnitude of charge, not the sign. So this term qb upon m whole square will give omega c square, square of angular frequency, and this angular frequency is known as cyclotron frequency, and we write it as omega c equal to qb upon m. These two equations 12 and 13 are like those of equations of simple harmonic motion. Equation of simple harmonic motion is x double dot plus omega square x equal to 0. And we can write the solution of these two equations 12 and 13 as Vx. Vx is the solution of this equation. Equation 12, that is for Vx double dot. Solution of this equation is Vx, and Vx is equal to V perpendicular, that is some constant, e to the power plus minus I omega c t. We write qb upon m whole square as omega c square. Then solution for Vx for this equation 12 is given by Vx is equal to V perpendicular e to the power I omega c t. Omega c is qb upon m. Solution is e to the power I omega c t, and there are two solutions. One is e to the power plus I omega c t, and other is e to the power minus I omega c t. So the two solutions are e to the power plus minus I omega c t. V perpendicular is some constant known as amplitude of these components Vx and Vy. Similarly, we can write solution for this equation 13, that is for Vy double dot. This gives solution Vy, and we write these two solutions by this single equation Vxy. If we write Vx, it is the solution of equation 12, and if we write Vy, it is the solution of equation 13. These two solutions are written combined by this single equation Vxy equal to V perpendicular e to the power plus minus I omega c t plus I delta xy. Delta xy is also a constant which represent the phase. Here V perpendicular is positive constant denoting the speed in the plane perpendicular to B vector if phase delta is chosen such that delta x or delta y, these are the phase for solutions Vx and Vy. This equation actually represent two equations, one for Vx, then we have delta x, other is for Vy, then we have delta y. This phase delta, whether it is delta x or delta y, if we choose this phase delta such that Vx equal to V perpendicular e to the power I omega ct, we take positive sign in e to the power plus minus I omega ct, then we choose this delta for solution of Vx as 0. If we choose phase delta such that, then we write Vx equal to V perpendicular e to the power I omega ct, and this is equal to x dot. Px is the x component of velocity and it is dx upon dt, which we write as x dot. Then from equation 6 we get Vy equal to equation 6 is this equation mvx dot equal to qbvy, and this gives Vy equal to m upon qb Vx dot. So Vy is equal to m upon qb Vx dot, and we put the value of Vx dot. Vx dot is differentiation of this Vx with respect to t. So in this solution we must write Vx is equal to V perpendicular e to the power plus minus I omega ct. We here in this equation 17 removed this sign plus minus before I omega ct. Correct this relation, we write Vx equal to V perpendicular e to the power plus minus I omega ct. We write only delta equal to 0. We choose delta such that for Vx this delta is 0. So Vx is V perpendicular e to the power plus minus I omega ct, and Vy is equal to m upon qb Vx dot. So value of Vx dot is put from this equation differentiating Vx with respect to t. If we differentiate Vx with respect to t, then from this relation Vx dot is V perpendicular is constant, and here is e to the power plus minus I omega ct, and differentiation of this with respect to t is plus minus I omega c e to the power plus minus I omega ct, and it is equal to plus minus I V perpendicular e to the power I omega ct. Here before the bracket we write m upon qb. If we bring m down to denominator, then we can write it as 1 upon qb upon m, and this qb upon m is omega c. So in the denominator we have qb upon m, which is omega c, and this omega c cancels this omega c. and we get plus minus I v perpendicular e to the power plus minus I omega ct, and this is y dot. Vy is equal to y dot. We write Vy as y dot dy upon dt. So y dot, that is dy upon dt, that is Vy, it is equal to plus minus I v perpendicular e to the power plus minus I omega ct. Integrating equations 17 and 18, we get 17 and 18 are equations for x dot and y dot, that is for dx upon dt and dy upon dt. If we integrate these two equations for x dot and y dot, we get x and y. And if we integrate, integral dx is x, and if we put the limits, it comes x minus x0. x0 is the initial value of x at t equal to 0. Similarly, by integrating the other equation for y dot, if we integrate that, we get y minus y0. y0 is also the value of y at initial time t equal to 0. So by integrating these two equations, this is equation 18 for y dot, that is dy upon dt, and this is equation 17 for x dot. X dot is dx upon dt. If we integrate these two equations, we get x minus x0 and y minus y0, as x minus x0 comes equal to minus I v perpendicular upon omega c e to the power I omega ct. If we integrate this relation, integrate e to the power I omega ct, v perpendicular is constant. Integration of e to the power I omega ct is equal to 1 upon I omega c e to the power I omega ct. And 1 upon I is equal to minus I. So we get x minus x0 equal to minus I v perpendicular upon omega c e to the power I omega ct. Similarly, for y, we have y minus y0 equal to v perpendicular plus minus v perpendicular upon omega c e to the power I omega ct. By integrating this equation for y dot is dy upon dt, and integration of this equation gives value of y minus y0. Now we define Larmor radius as RL, L for Larmor, R for radius. If we define Larmor radius equal to v perpendicular upon omega c, v equal to omega r, this is the relation between linear velocity and angular velocity, v equal to omega r. From this relation, we have r equal to v upon omega. So we define v perpendicular upon omega c as RL, and it is termed as Larmor radius, and it is equal to mv perpendicular upon qb. Put the value of omega c. Omega c is qb upon m. So we define RL equal to v perpendicular upon qc. Put the v perpendicular upon omega c, and put the value of omega c, that is qb upon m. Taking the real parts of equation 19 and 20, we have, then these two equations becomes x minus x0 equal to RL sin omega ct. Put v perpendicular upon omega c equal to RL, and take the real part. If we take real part, then we must write e to the power I omega ct as cos omega ct plus I sin omega ct. And separate the real and imaginary part. Imaginary part is that which have the term I, and I square is equal to minus 1. So we have two terms here and real part is RL sin omega ct e to the power I omega ct. We must write it as cos omega ct plus I sin omega ct. And then real part comes x minus x0 equal to RL sin omega ct. RL is V perpendicular upon omega c, which is Larmor radius. Similarly, for y minus y0, we have plus minus RL cos omega ct. These are two equations for x and y. Equation 22 and 23. This describe a circular orbit having fixed guiding center x0, y0. These two equations for x and y, these two equations describe a circular orbit having fixed guiding center x0, y0. x0, y0 is a fixed point known as guiding center. So in this diagram we see this guiding center is a fixed point having coordinates x0, y0, and that is the initial position. Initially x equal to x0 and y is equal to y0. So this initial position is termed as guiding center having coordinates x0, y0, and these two equations describe a circular orbit having fixed guiding center. The direction of gyration is always such that magnetic field generated by charged particle is opposite to that of externally imposed magnetic field. Now, if charged particle is positive, it will move in circular orbit. If charged particle is negative, then it will also move in circular orbit. This cross indicates the direction of B vector, direction of magnetic field, and it is perpendicular to this plane of paper. So motion of charged particle will be in the plane of paper, and this motion is circular motion. Positive charged ion move in circular path in anti-clockwise direction, while negatively charged particles also moves in the plane of paper in circular orbit, but now they move in clockwise direction. If positive charge moves in anti-clockwise direction, negative charge will move in clockwise direction. The direction of motion of this charge is such that if this motion of charged particle produce magnetic field, then that must oppose this externally applied magnetic field. Magnetic field due to motion of this ion must be in opposite direction to this B vector. So these positively charged ion and negatively charged particle moves in opposite directions. Plasmas are diamagnetic as plasma particles tend to reduce magnetic field. If charged particle moves in such a way that magnetic field produced by them is in opposite direction to externally applied magnetic field, then this motion will reduce the net magnetic field, and such materials are known as diamagnetic substances. Plasmas are diamagnetic substances as plasma particles tend to reduce the magnetic field. In addition to this motion, there is an arbitrary velocity Vz along the direction of magnetic field which is not affected by the magnetic field. The trajectory of a charged particle in the presence of magnetic field is in general a helix. Helix is a circular motion, and the charged particle moves in circular motion and also moves in the z direction, also in the direction of magnetic field. So the trajectory of charged particle will be in general a helix.